At the outset, I would like to remind you that the problem that we were considering for a nonlinear spring was just a representation of how to set up a nonlinear problem. But if in the solution methods that I want to bring forward today, or even in the few lectures from now, or in the few videos from now, I want to make it clear that the nonlinearity or the type of nonlinearity, the source of nonlinearity is not the important point of the present discussion. It's important to understand that we have a nonlinear equation where you have a certain dependent variable and you want to find out the behavior of one of the terms with respect to this dependent variable. In this case, if you have a load displacement, you want to find out the load with respect to the displacement, which is sort of the dependent variable in the system. So don't worry about which kind of nonlinearity it is. The solution methods that are applied are generic. So let's consider the equation again that we have been looking at. So if I start with Ku is equal to F, then I want to assume for now as an example that K is dependent on U. That means K changes when U changes. However, there may also be examples where F changes when U changes. These kinds of examples I've already expressed to you before, that there might be a change in the direction of the structure as it deforms, so the loads are going to change. So if the load changes with respect to the displacement, then of course it's also displacement dependent. Now there are many solution methods that I will bring forth one by one to you, but for this particular video we will consider the most commonly used solution principles and the most mature ones. I'm quite certain that at some point in your life while you were studying or you were going through some mathematical or numerical analysis or calculus texts, you have come across these methods. However, we will put them now into application, into context, so I hope your answer of why are we studying this maybe in the past are also answered in an engineering context. The first method that I'm going to explain to you in terms of one of the solution methods for nonlinear problems, or let's say time-dependent problems, is known as the Newton-Raphson method. So this is the first one. It's called Newton-Raphson method. Now in calculus text, you may be introduced to these terms also simply as Newton's method, and they are generally explained as a way of extracting the root of a polynomial. But in this case, we are going to show you this method as a way of generating the load versus displacement curves of whose shape we do not know at the outset. So we have a certain problem that we need to solve, and we know that it's going to be loaded and it will deform under that load, but we don't know how exactly that will happen. Let us consider the nonlinear spring problem again and say that for this problem condition, K U is equal to P is the standard equation that we are going to solve. Now, because we are using the Newton-Raphson method, we do not know what the P versus U curve is going to be like. So we start with certain assumptions. Let us take, for example, that we start with the load level 0, then the initial displacement U is taken to be 0. Now, if we apply a certain load P1, let's say the value, the level of P1 is here on the graph, and you're going to apply a certain value P1 as the first load level, then we will have a corresponding displacement that we are looking for, which will be given by U1. So I can easily write when load P1 is applied, so that's the initial load I want to apply, displacement U is equal to U1. Now we know that before, when I was describing how to set up these problems, we also got introduced to the term called the initial tangent stiffness. So whenever there's a change in load, or when a local change in load with a local change in displacement, we can find out the tangent stiffness for the load displacement curve at that instantaneous point or instantaneous time. So in this case also we can find out the initial tangent stiffness given as k, don't want to write there, kt0. So in this case, I need to know, to define this initial tangent stiffness, I need to know what is the initial load increment and what is therefore the initial displacement increment. But that the displacement increment is the one that we are looking for, and that's the unknown in the problem. And we know that the load applied at the first step is P1. Therefore, the change in displacement, or the first displacement increment delta P1, can be given as the load P1 minus the initial load, which is 0. So we can easily write the tangent stiffness kt0 times the change in displacement delta u is given as the change in load delta P1. Therefore, delta u can be given as the inverse of the tangent stiffness at the initial load point times the initial load increment delta P1. Now, if I easily, what I would like to do is I would like to show you graphically over here what happens. So if I have a certain load P1 which is applied initially, I can find out the tangent stiffness based on the relation that I just described to you. So if I draw the tangent stiffness over here, then it's just linear tangent stiffness such as this up to point P1, up to load level P1. I hit a point here which I call point A, and I know that this is just an initial tangent stiffness. It's not the actual tangent stiffness which should be for that certain point in time for this problem, or for this system, or the linear spring in our case. So I know for a fact that this system is therefore not in equilibrium. If it's not in equilibrium, then an error can be calculated for the current load. So I'm going to go to the next page and write this down. So that means I can calculate an error for the current load, which I can call EPA because I hit the point A. And this error is going to be found out by using the equilibrium equation. So I had Ku is equal to P. Therefore, the error can be found out as the load P, which is in this case load P1, minus the stiffness times the displacement UA. Now, another thing to note here is that here when I have hit the point A with my tangent stiffness on the P1 load level, this corresponds to a certain calculated displacement UA. Now, because this doesn't make it in equilibrium, I'm calculating the error by taking the displacement UA as the current displacement calculated. Here, the stiffness K is a function of U, and this is calculated at U is equal to UA. So it always leads to a certain error, EPA. Once I have calculated this error, I can remove this error from the system. That means I can calculate the error, and I know that the error is, let's say, somewhere here, EPA. Let's make it a little bit shorter so we don't have to do too many steps. If I say this is EPA, is the amount of error, and I draw this very simple line here, then I need to drop down up to this point, which gives me the new point A. So my solution actually is going to be from 0 to A for now. But we haven't still reached the first load step P1. Therefore, we must carry out another iteration. So at this point where I've hit point A, I will continue drawing the tangent stiffness along this point now, because that's my new tangent stiffness. So I will take it up to P1 again. And I will get this new value of U. I'm following the exact same method as I did before. Now I have UB. I will calculate the error, and let's assume that in this case the error comes out to be close to 0. So I stay at the same point as point B, which basically now becomes my point 1, and my result is here. That means I had no error. So this becomes my final, this becomes my curve up until point P1. In the same way, I can also say now I'm going to apply a second load increment, and the load increment will be such that the final load becomes load P2. Now here I would like to show you some more steps to make it, to explain it again, and then I will write down the mathematics or the way I calculated it afterwards. So we say again that I want to find out the tangent stiffness. Now in this case, my delta P2 is going to be the change in load from P2 to P1. And I already have my new displacement, which now I can call displacement very close to UB. It's called displacement U1. Now this displacement is the final displacement at the load level P1, which is what we were looking for in the first increment, let's say. And within the first increment up to load P1, we calculated a number of iterations, and in this case there were only 2 iterations that were required. Now we do a second increment, which is up to load P2. So the change in the load is P2 minus P1 or delta P2, and I need to find out now the new displacement. So I'm going to again continue with the same method. I'm going to say that there is a certain tangent stiffness which comes out of which is KT1, and by plotting this certain tangent stiffness, I end up at a certain point C on the increment line P2. This corresponds to a certain displacement UC. However, there's definitely an error which we must remove, and this error is error PC, and this error is up to here, so it's a large error from the point you want to be at. So you see that we come up to a point right here, so I can draw the line from there to there. So this is what the change in the displacement with respect to the load is. And now at this point, I continue drawing the second, with the same slope, I will draw the tangent stiffness again. I will end up at a point D, which is going to give me a displacement of UD. I will always find an error again, which will be given as EPD in this case, which comes up to this point. I will bring down this case also I had to remove the error from it to come back. This would be my new point, so I can join this here. And then I will continue making the same slope, always up to P2. This would be point E, and here I would most likely find an error, hopefully that is 0, and I would say this is now my point 2. So I can get a displacement. Let me do it with black as before. U2. So now I have at load level P1 a result U1, and at load level P2 a result U2. Now let's write some equations down to make this clear as well. Now we did everything up to the error for EPA, which is given here in this graph. And while we were calculating EPA, and we found out the new tangent stiffness after EPA, it would be the KTA. I would write it like that then. KTA delta U would be equal to the error. That is what we did. We just reduced up to that point. So we could easily find out the change in displacement as the inverse of the tangent stiffness at A with the error at capital A. So we got a new displacement UB to be equal to UA plus delta U, which is quite clear here. So we had the EPA was taken as the error. So that is of course going to give you the difference in the stiffness with the displacement. So that makes clear sense to you, I hope, because EPA is nothing but also a change in the load. And if I multiply that with the inverse of the, that would be equal to the tangent stiffness times the change in displacement, according to the definition of tangent stiffness. So here we got the delta U to be equal to the K inverse times the error at PA, and therefore the UB would be equal to UA plus this change in delta in between the two. So I hope that is clear to you, because it just continues in the exact same way. If it's not, of course, we can get back to this in discussion in the online group session, or also on discussion board. It's absolutely no problem to have this discussed over again and again through the course. So now we have the new UB, and we find out that maybe this is not an equilibrium, so we try to find out an error at EPB is equal to P1 minus the stiffness times UB, where this stiffness K is dependent on U and is found out at UB. U is equal to UB. So we see that when I calculate this value, this comes out to be 0, therefore the error is 0, therefore the displacement UB is actually equal to the displacement that I was looking for, which is U1. And in this way, I find out that when, we write this in different color, when load increment is delta P1, a number of iterations are needed within this increment to get the final result U1. So there are two terms now that have been introduced to you. One of them is the load increment, and the other one is iterations, or number of iterations. These are very important in a nonlinear analysis. Now, to continue further in the same scene, we did a second iteration, a second load increment. So we had a load increment delta P2, which was given as P2 minus P1. In this case, we can also write that the tangent stiffness at the point 1 times the change in displacement would be given as the load increment delta P2. We can easily find out delta U to be equal to KT transpose delta P2. And we end up getting a new displacement UC, which is given as U1 plus this delta U, which was calculated here. And that is exactly what we showed in the curve. Here we had the tangent stiffness KT1, and that corresponded to a displacement UC, which gave us an error EPC. So you get UC, which is equal to U1 over here, plus this delta U. Now it's going on in the exact same way. Just for the sake of completeness, I want to write this down for you. We would also find EPC, which would be given as P2 minus KUC. So of course here K is also dependent on U, and it is calculated that U is equal to UC. We find, of course, there is an error. So we find this error, we bring it into the next equation. So we find that the tangent stiffness KTC times delta U is given as EPC. So we plot this, of course, we have a delta, we find out the delta U in this case, which is given as the tangent stiffness inverse EPC. And with this change in U, we can find out now UD is equal to UC plus delta U, and so on and so forth. We can calculate up to the point where we get the error to be equal to 0, which happens to be assumed to be at point E, which is the next iteration. So therefore UE becomes equal to U2, which is the displacement we were looking for at the next load increment. This in general describes to you the Newton-Raphson method. So we need a lot of equilibrium iterations to be able to get to a solution within a certain load increment. So clearly, if we apply a sequence of increasing load levels and we iterate to convergence for each of these load levels, so we kept iterating till we got to the point, then, so by convergence we mean reducing the error, or E, so that we are every time at a stage of equilibrium, we are able to construct an adequate P versus U curve or F versus U curve in a problem. Of course, the likelihood of reaching convergence to a correct solution for every problem is not guaranteed by using this method. The chances, however, of getting or converging to a correct solution increases if you reduce the size of your load levels. So the smaller load levels or smaller increments that I choose in my problem, the better chances I have of getting to the most adequate or the most correct converged solution for the equation I'm trying to solve.